Okay, great. Yeah, thank you. Thank you for the introduction, and thank you so much for inviting me here to share some of the work that we have been working on the fault-tolerant quantum computing. So my name is Meng. I'm from the University of British Columbia. I'm currently a PhD candidate, and my work is focusing on system optimization for the entire quantum computing stack. And we have started working. When I started my PhD, we had some works in the variational quantum algorithm that is more focused on the disk era computing approach. And more recently, we have been shifting our focus and working on the fault-tolerant quantum computing. So let me get started here. So we know that the today's quantum devices are quite noisy, and those high level of errors that are really preventing us from executing any reliable quantum algorithms. So one of the main solution to that, or one of the main approach to tackle those noise challenges nowadays, is using quantum error correction codes, where we use multiple physical qubits to encode one logical qubit. And during execution, those redundancy enable us to actively detect and correct errors. By using those quantum error correction codes, not only do we have those additional physical qubit overhead, we also have a constraint on what kind of logical operations that we can apply. Usually, there are different kinds of quantum gates that can be applied fault-tolerantly, but most common used gate set, what we use is, first of all, those Clifford gates, the single qubit Hadamard and phase gates, and then the two qubit CNOT gates. Those can be natively supported by most of the quantum error code, like the surface code, or even some of the QUBC code through some special mechanisms. But the Clifford gate themselves are not universal, so can't perform universal quantum computing with just these three gates. We do need the addition of one non-Clifford gate, and the choice for that usually is the single qubit T gate. The problem with this is that while it enables the universal quantum computing and universal fault-tolerant quantum computing, but it cannot be directly implemented in most of the quantum error correction codes. To do this, there was this approach where, well, instead of directly apply this gate, we first prepared this so-called a magic state on some ancillary qubit, on ancillary logical qubits. Once we have this special state prepared on the ancillary qubits, we can do the state injection onto the target qubit. And throughout this state injection process and injecting the magic state onto the target qubit, the effect on the target qubit is as if we applied the T gate directly on the target qubit. So for those logical gates, there's a cost associated with each of them. So usually though there are two dimensions that we can measure the cost. The first dimension is the space cost, which is typically the number of qubits you would need to realize this operation. Another direction is the time cost, which is usually measured as the QEC cycles. And first of all, the cost of those two Clifford gates, the single qubit Hadamard and the CNOT gates, they are moderate. They have moderate costs in both the space and time directions. The phase gate is especially in the surface code case, the phase gate is notably more costly than those two other Clifford gates, but still they're having a comparable cost in the both dimensions. The T-gate itself, assuming you already have the magic state prepared, then doing the state injection onto the target qubit to perform the T-gate is actually comparable to just doing a single Clifford ASK gate. The true problem or the challenge actually arises from preparing such high fidelity magic states. So those magic states are very costly to prepare, and conventionally they're prepared using some distillation process where you have initial magic states that are prepared through some noisy process, and you have multiple copy of those noisy magic states. And then you can do distillation to distill multiple noisy copies into one superior less error copy. So this is very costly to prepare such magic states. So put in context, here I'm showing that the cost of magic state preparation, where the x-axis I'm showing the qubit cycle volume. This is generally the metric where we measure how costly a fault-tolerant operation is, and the higher the volume, the more cost associated with that. And the y-axis shows the logical error rate we're trying to achieve, because here what we're trying to get is the logical operation, so we can always put in more resource to get a lower error rate, and also the cost of a logical CNOT is plotted for reference. So I mentioned that initially we're using this distillation process to produce those magic states, and that is very costly. But there have been several advances in this field that try to optimize the distillation protocols, where it propose other types of approach to minimize the cost of the preparation of those magic states. We're actually seeing great progress in this field. So initially from a 2012 proposal, the cost of a single magic state is several orders of magnitude higher than those Clifford gates. So fast forward to 2020, we have seen some improvements in optimizing the distillation protocols, and they bring down the cost of those magic states substantially, but still we're at least at an order of magnitude higher cost than logical CNOTs. But in 2024, Gitney proposed this method called magic state cultivation, which in theory could bring the cost of magic states close or even below a Clifford gates. Well, I have to mention that this is the theoretical cost of this cultivation proposal. When you're trying to actually use such protocols, there are actual implementation limitations which can increase the cost of those magic states. But still, the overall trend is that we can, in theory, put the cost of those magic states pretty close to the Clifford gates. So we have seen that this is a dramatic cost dynamic change in the entire Clifford MT gate sets. To put this into context, if we're measuring the Clifford overhead here I'm using an 18-qubit QFT circuit. So on the y-axis, I'm showing the Clifford overhead as a percentage of the total execution overhead. If we just use the 2012 cost proposal and use its cost dynamics, the Clifford overhead only accounts for 3% of the total execution overhead. That's why most of the papers in the past decades or so, mainly just focusing on optimizing the T-gate itself. And we fast forward to 2020, we can see that from those improvements in the magic state preparations, we do see a slight increase in the overall Clifford overhead, but still it's only account less than 5% of the total execution. But if we bring in the most recent chart, that is actually significantly bring down the cost of those magic states, and that in turn has made the Clifford overhead actually become the dominant cost in this example circuit. So right now we are entering a stage where we can no longer just overlook the cost from Clifford gates, where previously we think those are just negligible costs. Well, for those Clifford costs, there are actually ways to tackle them completely. So the method is called the poly-based computation. The idea is that we first convert all those Clifford MT gates into the form of so-called polyproduct rotations. So for each of those rotations, we have a rotation basis. When dealing with those logical qubits, we have the three bases, X, Y, and Z. And here we only have X and Z rotation basis for those gates. And each rotation operator will also have a rotation angle associated with them. So for all Clifford rotations, there are pi over 2 rotations. And for the non-Clifford rotations, it's pi over 4 rotation. So what PBC works is that given any Clifford NT circuit, first we convert this circuit into this polyproduct circuit. So we only have those polyproduct rotations. Then for each of the Clifford rotations, those lighter color blocks, we can conjugate or commute them through all the non-Clifford rotations, the darker ones. So we can commute through them, and those Clifford rotations will be at the all group at the end of the circuit. Once they are at the end of the circuit, they can be merged into the measurements. So there's no cost associated with any of those Clifford rotations. But the effect of this is that they're going to transform those originally just single qubit non-Clifford rotation because originally we only have T gates. Those T gates are just single qubit gates. Originally, those are all single qubit non-Clifford rotations. Now, some of them becoming multi-qubit non-Clifford rotations. This could affect the overall gate parallelism in your circuit. So if we measure that again with the same 18-qubit QFT circuit, if you just represent your circuit in your original Clifford plus T form, then on average, you have roughly 6 gates in parallel you can execute on average. But once you transfer to the PBC form, what you're getting is just on average, you can only execute just one operation. The reason for this is that once you convert to the PBC and eliminate all the Clifford gates to the end and merge into the measurement, most of the non-Clifford rotations are now involving more than half of the logical qubits. So you can think that, oh, if this operation require more than half of the logical qubits and the other also require more than half of the logical qubits, then there's only one of them you can apply at any given time. So this is not ideal. This can actually hurt your overall runtime and can make your overall execution FTQC volume, the cost even higher than the original Clifford plus T. So our approach, this was published in ISCA 2026, which we propose a transponder architecture co-design to curb those Clifford costs in the fault-tolerant quantum computing. The central idea or the central pieces of optimizations in our approach is that we want to do a targeted Clifford optimization. And it includes 3 main parts. The first part is we want to target the Clifford overhead that is originated from those rotation synthesis. And then once we target that, the resulting circuit have some localities in the gates that there are in the optimized circuit. So we propose a locality-aware architecture that leverage this feature. And in the end, we also want to focus on the Clifford overhead that is from the top lead gates. So those are the 3 main targeted optimizations, and I'm gonna go through each of them. So first of all, the Cliffords from those rotation synthesis. Without jumping into what the rotation synthesis is, I'm gonna first show that whenever your quantum algorithm or quantum circuit contains rotation gates, the single qubit arbitrary rotation gates, then once you convert those circuit into Clifford plus T form, the majority, almost 99% or more of the Clifford gates are actually result from those rotation synthesis. The reason behind this is that for those single qubit rotation gates, what we're generally talking about are the ones like RZ, RX, or RY, and they can be interchanged with some additional Clifford gates. So here we just take RZ gates as example. Those RZ gates cannot be directly lowered into just Clifford plus T form. So they have to be synthesized into the Clifford plus T form. And the algorithm that is used to do this, right now the state of the art is the Graythins algorithm. What it does is that it can synthesize a Clifford plus T gate sequence to an arbitrary accuracy for any given rotation gates. But in the end, from each rotation gate, we're going to end up with dozens to even hundreds of gates from just a single rotation gate. And among those dozens or hundreds of gates, 60% of them are the Clifford gates. So you can imagine that if you just have a few rotation gates in your circuit, you can easily have hundreds of Clifford plus T gates in your final circuit. So this is a huge overhead in terms of the Clifford part. So we want to focus on this first. So for any given Clifford plus T circuit, the first step our method does is that it first gather all the single qubit gate sequences. And among those gate sequences, many of them are actually from those single qubit rotations, but we don't just constrain to the ones that are actually from the rotation synthesis. We target all the single qubit Clifford plus T gate sequences. So as the first step, if you're just looking at those gate sequences, there are just too many possibilities that exist. So we can't really do a very straightforward or effective optimizations just by looking at random gate sequences. As a first step, we do want to represent each of those gate sequences into a form that we first want it exist for any of the single qubit gate sequence we're given. We also want to make sure that this gate sequence is unique. And most importantly, we want to make sure that this gate sequence guarantees T-count optimality. So once we want to represent any arbitrary single qubit Clifford plus T gate sequences in a form that guarantees those three characteristics that enables us to do more efficient optimizations as next step. Well, there was this form that exists that has all those three features. This is called the Matsumoto Amano normal form. So what this form looks like is that for any sequence that is represented in this form, it always starts with a leading T or not. So this is the optional leading T. And then after this optional leading T, we can have either the HT sequence or the SHT, and we can have alternating number of them. Again, here we can have arbitrary number of each of those two sequences. And then in the end of the sequence, we have an optional Clifford gates in the end. So we can see that it's a very structured form, and it guarantees the three features that we just discussed. So as the first step, we're converting all the single qubit Clifford plus T sequences into this form. We can see that except for the first one, all the rest of the three are already in their normal form. Whereas for the first one, it actually, by doing this transformation, we reduce the two T gates plus one phase gate into a Pauli gate. So we already see some benefits from just converting to this normal form. So by looking at this form, the first gate we want to address is the phase gate. We mentioned that this is the most costly Clifford gates among the three of them. So we want to target this. So from this form, we can see that there's only a very limited possibility that this gate can exist. First possibility is that we do not have the leading T, and then immediately start with the SHT sequence. The second case is that we do have a leading key, and then followed by this SHT. The third case is that in the middle of the sequence, we first have an HT sequence, and then followed by the SHT. The last case is that also in the middle, we have SHT followed by another SHT. You can see that out of the four only possibilities that this phase gate can exist in this sequence, three of them are showing this TS gate pattern. So what this TS gate pattern is interesting to us was that it actually is equivalent to this. So it's equivalent to ZT dagger. So there are a couple of ways to prove this. So, but I think the most straightforward way is just all of those three types of gates are Z basis rotations. So we can represent the S gate as two T gates, so T squared. The Z gate is four T gates, so T to the fourth. The T dagger is just T to the minus one, the inverse. So the TS is actually just T times T squared, that is the S gate, and they end up being the T to the third power. And to T to the third power is actually just T to the fourth times T to the minus one, which is Z gate times the T dagger. So there are other ways to prove this. You can also write down their gate matrices and multiply them and see that, oh, they do end up with the same gate matrices. But this is one way to demonstrate that. By doing this conversion, the Z gates, those Pauli gates, they are zero cost in most of the error correction codes. They can be tracked in software, so they don't have any implementation costs. The issue might be associated with the T-dagger gate, but not from the implementation point, because when we're trying to apply the T gate, what we're doing is we first, as mentioned, that we prepared this magic state on some ancillary qubits. Then what we do is that we do the joint ZZ measurement between those two to do the state injection onto the target qubit. After we do this joint ZZ measurement, what we're getting on the target qubit at this point is T or T dagger effect with equal probability. So if the gate you're trying to get is not the same as the one you're actually getting, you can just correct this with another Clifford gates. So by doing this, you can see that actually from the implementation or the execution perspective, the T and T dagger gates, they're having the same cost. So back to our gate pattern, the TS gate, once transferred to this, one of them is zero cost and the other has the same cost as T. So we effectively transfer the costly Clifford phase gate into a zero cost poly gate. And from our previous, from all the possibilities of the phase gate, we can make the conclusion that there can have at most one phase gate left in each single qubit gate sequence. That's the case when we don't have the leading T gate and immediately start with the SHT. For the rest of the cases, they all have this TS gate pattern. So all of those phase gates can be removed this way. So we're taking this gate sequence as example. As the first step, we do this TS to ZT dagger transformation. Then the second gate we're focusing on are the Hadamard gates, because that's only left, the only gate, Clifford gate left that is having some actual execution costs. For the Hadamard gates, what we do is just we conjugate all the Hadamard gates to the end of the sequence. And during this conjugation, what those Hadamard gates, the effect of them have on the other gates is that it swaps the rotation basis between X and Z. So initially we have the poly Z gate. Now that becomes X once we move the Hadamard through it. And the T gate, originally it's just RZ pi over 4 rotation. Now it becomes RX pi over 4 rotation. Once we put all the Hadamard to the end of the sequence, we can just cancel those Hadamard gates pairwise because Hadamard are self-inverse. So two of them just cancel to identity. So this is what we left. Again, we're going to have at most one Hadamard gate left. Then that's the case when you have an odd number of Hadamard gates in your sequence where rest of the Hadamards are canceled pairwise with one left. And if you have even number of Hadamard gates in your sequence, then all of them just cancel pairwise. So our original circuit from this form is transformed to this from the optimizations we just discussed. So for this particular example, the non-trivial Clifford gates reduced from 8 to 4. And back to the rotation gate sequences, we have shown that initially we're going to have those dozens of hundreds of gates. And after this single qubit rotation gate synthesis optimization, what we're getting in the end is we may have a single phase gate in the beginning and then followed by TRX, TRX. So each of those darker blue gates, they're all pi over 4 rotations. Just the T are the Z basis rotation and RX are the X basis rotation. So let's see how they can be implemented. So we did introduce this new rotation, non-Clifford rotation gates into the gate set, but it's actually pretty similar to the original T gate. So for the T gate, I mentioned that we do the joint ZZ measurement between the target qubit and the magic state ancillary qubit. To implement the RX rotation, what we need to do is just do the joint XZ measurement instead of the ZZ. And again, with the same magic state ancilla and on the target qubit. So we can actually also, if we can natively do the T gates, we can also natively do the RX gate on most error correction codes. And the hardware-software co-design we're thinking is that we do see that we have this sequences of dozens of non-Clifford rotations just on different logical qubit bases. And each of them going to consume one magic state. So let's see how we can address this. So here, some example logical qubit is to look at this. We usually abstract this logical qubits with a qubit patch or a block, where on the edges we show the logical operators of this logical qubit. Here, the top and bottom are the logical X operator of this logical qubit. And on the left and right boundary are the logical Z operator. To do this joint ZZ measurement, usually we can do that using lattice surgery. What we need to do is we do the lattice surgery between the logical Z operators of the target qubit and the magic state ancilla. We can do this through some ancilla qubits, but we can also directly do that. But most of the time, those magic states, once prepared, are far from the target qubit. So we do need to route through some ancilla qubits to realize this joint ZZ measurement. So we do the lattice surgery between the logical Z operators of both target qubit and the magic state ancilla. To do the logical joint XZ measurement for the RX rotation gates that is introduced from our optimization, what we need to do is we need to do the lattice surgery between the X edge of the target qubit and the Z edge of the magic state. So here we need additional ancilla routings, and we can do the surgery through this pass, and this enables us to do the joint XZ measurement, which realize the RX rotation. So generally, you can see that there are different kinds of architecture designs for the current fault-tolerant quantum computers, but usually you can imagine something like this. So you're gonna have your logical qubit patches stored in some place, and they're gonna have some ancilla qubits also in your architecture that is responsible for routing those logical qubits with other resources like the magic states. Those magic states are usually being prepared by some costly magic state factories, which require a large qubit footprint. So those magic states, once prepared, are usually outside your typical computing region. So I'm showing it here as an example. So for any logical qubit that is trying to consume this magic state, you're gonna require ancilla routing between itself and the target magic state. And if we just continue with this fixed architecture design, then for the sequences of T and Rx rotations that we introduced, for each of them, they're gonna allocate the same ancilla path over and over again for those dozens to hundreds of gates consecutively. And also we need to do patch rotations because in this case, for each logical qubit, only one logical edge is exposed to the ancilla region. So if we want to access a different logical operator of any target qubit, we need to rotate this patch to expose a different logical edge. So those two operations are very costly, so they can block the execution of other logical operations as well. So we introduced this so-called compute block, where we have a compute qubit that is sit very close to the magic state factories. And for this entire block, once you move a logical qubit to this QC, it has both logical Z and logical X edges exposed through ancilla to the magic state. So it can consume the hundreds of magic states without doing any patch rotations. And during this time, you're not blocking the execution of the other logical operations that is in your circuit. Because remember that although we have eliminated most of the Clifford gates, there are still remaining Clifford operations in your circuit. And once those qubits are consuming the magic state in the compute block, rest of the qubits can carry on with those other logical operations. And those ancilla paths during this time can also be used for other purposes. So this is the hardware-software co-design we think that could benefit from this gate locality. So the third optimization is the Toffoli, the Clifford overhead from Toffoli. So if you're familiar with the fault-tolerant quantum computing, the Toffoli gate can be think of the single most important logical operation in the fault-tolerant quantum computing. For many of the arithmetic algorithms, it's heavily relies on the Toffoli gate. And here I'm showing a couple of them. And if you have those arithmetic circuits, once converted into the Clifford plus T form, about 70% of the Clifford overheads are actually from the Toffoli decomposition. So the Toffoli gates itself are the 3-qubit CCX gate. It, unlike the rotation synthesis, it has exact Clifford and T representations. So each Toffoli gate can be exactly decomposed into 15 gates, Clifford plus T gates, out of which about 7 of them are the T or T dagger gates, and 8 of them are the Clifford gates. And you can directly see from this decomposition that any of the single qubit optimization method we introduced before doesn't really apply here. So we have to figure out a new way to get rid of the Clifford overhead for Toffoli gates. So what we're doing instead is that, well, let's first just commute all the Clifford gates through this sequence and group them together. So for example, for the first 2 Clifford gates, the Hadamard and the CX gate, we can commute them through the first T dagger gate. And this is the end result. So the T dagger gate now becomes ZX, the multi-qubit non-Clifford rotation, and the Clifford gates remain unchanged. We can do this for all the Clifford gates and group them to the end of the circuit. And this is what we're getting. We see that some of the, as in the PVC case, some of the non-Clifford rotations now become multi-qubit non-Clifford rotations. But first, let's focus on the Clifford gates that are grouped in the end. As the first step, we can swap those 2 CNOT gates because they commute, meaning we can just freely reorder them. And now we see this pattern because CNOT gates are also self-inverse. So if we have pair of CNOT gates, we can also just cancel them pairwise. And once we cancel all the CNOT gates, the 2 Hadamard gates can also be canceled pairwise. So we actually, by doing this, we can get rid of all the Clifford gates. Although we're not having those multi-qubit polyproduct rotations, they are only constrained locally to those 3 qubits that the Toffoli gates apply to. So they do have slight effect on the overall gate parallelism, but not not amplified to the entire circuit level. So the overall gate parallelism is remain on a similar level of the original gate circuit. So for the evaluations, we did evaluations on both the rotation heavy and arithmetic circuits. So here I'm showing the number of qubits and number of our original gates. And I'm also showing the Clifford plus T gates, that is for the rotations, that is after synthesis. And for the arithmetic circuits, their Toffoli gates are decomposed into the 15 gate setup that we just showed. And you can see that for the rotation heavy circuits, each of them are having almost 100 times or higher gate expansions by converting from the original gates into the Clifford plus T, and most of them are originated from those rotation synthesis. But for the arithmetic circuits, their gate expansions are much more manageable. And the first result I'm showing is the Clifford reduction ratio. For those rotation heavy circuits, we can see that we can achieve almost 100% Clifford reduction, because we can eliminate most of the Clifford gates in those. But for those arithmetic circuits, because those are containing more number of CNOT gates in them. So those CNOT gates we can't really deal with them. So this is what we end up, but still we are achieving 80% or higher, around 80% or higher Clifford reductions. The more importantly, we're doing this without sacrificing the entire gate parallelism. So we have almost the same gate parallelism as the original Clifford plus T circuit. So overall, the runtime of our proposal, along with the hardware software co-design, makes the entire runtime much better than just sticking to the either the baseline Clifford plus T or to the PVC case. So this is the Clifford optimizations that of our that work, and I do want to have a brief introduction of another work we had that is the focusing on the T-gate optimizations. So we did the Clifford optimizations. We also want to have a way to do more efficient T optimizations. By efficient, what I'm saying is that right now those T-gate optimizations they can introduce other kinds of overheads, and also those optimizations are very slow to run. So we want to make them both more generating less number of other kinds of overheads, and also make those T-gate optimizations much more efficient. So to start, I want to introduce this ZX calculus, which is a very well-known method that can reduce the number of T-gates. But the ZX calculus, although it can reduce the number of T-gates, by doing so, it also increased the cost of the Clifford gates. And I just showed that those Clifford gates are actually not free. And we can also see that the overall depth is increased. And this is the additional overhead that is introduced by optimizing the T-gate. There's also another overhead that is the runtime overhead. So running the ZX calculus inside it uses the graph, this so-called ZX diagram, to represent the circuit. And for those fault-tolerant quantum circuits, generally you can expect to have thousands or even hundreds of millions of gates in your circuit. And once you transfer that into this ZX diagram, that means you're going to have thousands or even hundreds of millions of nodes in your graph. And for those graph representations, they have a very irregular memory access pattern. So overall, from our evaluations, we found those ZX calculus based methods running extremely slow for especially scales very bad to those large circuits. So instead, we want to use a different circuit intermediate representation that can enable us to do a similar T optimization, but more efficient. So what we're trying to do is that we're going to stick to this polyproduct rotation representation. So here, each of them are converted from either the Clifford plus T or other types of fault-tolerant operations. So again, they're gonna each of them specify the rotation basis of the operation and also rotation angle. So here I'm only showing the non-Clifford rotations for simplicity. So as the first step, what our framework does is that it creates this so-called the commuting layers. So for those ordered operations, we create those commuting layers where within each layer, all the operations are commuted with each other. So within each layer, they can be freely reordered because they each commute pairwise with each other. So let's take just the first layer. Once we have those commuting layers, what we can do is we can do the in-layer rotation cancellation. And to do that, we first just locate the operations that have the exact same rotation basis. Because they have the same rotation basis, they can just be merged together, and their rotation angle, we can just add them up. So this is the end result. Because we're adding up two non-Clifford rotations, so two pi/4 rotations, when add up, they just add up to a Clifford rotation. Although we have emphasized that those Clifford rotations are also costly, but still their cost is considered much lower than those non-Clifford rotations that require magic states. So by doing this, we can effectively also doing the non-Clifford optimizations. And also you can see that by doing this process, we're not adding any additional Clifford overheads. We just merging the non-Clifford rotations into the Clifford ones. So there's no gate overhead from this. So we have addressed the first issue. For the second issue, we want to represent those circuits more efficiently. We can't really do this directly with the Clifford plus T circuit, but we are able to do this with this Tableau circuit IR for the polyproduct rotation operations that we choose to use. So for those, so there's this Tableau circuit, so Tableau data type. What this specifies is that it has two parts for each operation. We have the X part and the Z part, and also a phase case. And each of those are the binary values within them. So for each row, you can think of this representing one operator in your circuit. So this you can see that this is a very structured data type. So it has very good cache performance when running on the either a CPU or GPU based platforms. And also we can do if very efficient commuting layer construction and also merging checks that I just discussed. So this can enable very efficient executions of your or compilations of your Clifford plus T circuit. So to evaluate this, we actually choose 13 fault-tolerant benchmarks, and they span different qubit numbers and gates. So the first result I'm showing here is that as compared to the ZX calculus, how many T gates or the non-Clifford rotations we can reduce. Actually, we see that across the entire 13 benchmarks, we're getting identical T counts as the ZX calculus does. So we're achieving the same level of T optimizations. And we're doing this without introducing any additional Clifford overheads, because I showed that by doing the merge, we only canceling gates. We're not introducing additional gates. So this is the gate count. So we're doing a same T counts optimizations as the X calculus. And in fact, we have also tested with other T optimization methods. So some of them can achieve a lower T count to both ZX calculus and our method, but they doing so generally achieve by either introducing select qubits or doing some other mechanism. So by just constraint to the given number of logical qubits and without any other mechanisms, this is perhaps the best T optimization you can get. So we achieve the similar level as the ZX calculus. And for the T depth, because we're not introducing those additional Clifford overheads, we actually reduce the T depth. So the ZX calculus optimized circuit will have a mean of 1.7 times higher circuit depth than ours, and to a max of 3.2 times. So those are the optimizations. So the circuit we're generating is actually better in terms of the gate and depth as compared to the ZX calculus. The other aspect I mentioned is the compilation speed up. We can, as compared to here we're comparing to the QuizzX. So our method is implemented in C++. For the ZX calculus, the most common framework you may be heard about is the PyZX. So that's the Python implementation of that. So we do not want to have those performance difference that originate from the implementation language that is you use. So this QuizzX implementation uses Rust to implement the same optimizations. And you know that Rust is also a very efficient low-level programming language. So it also performs almost on par with the C++ raw performance. But still, with this faster implementation of that, we still achieve 74 times speed up. And for max, for the largest benchmark, actually, the benchmark 5 is the largest one we tested. We achieve a 1700 times speed up over the QuizzX. So the Tableau IR I just mentioned is extremely efficient when dealing with those very large fault-tolerant circuits. Another method, another thing you can do with the Tableau IR or the polyproduct rotations is that I mentioned that there's this PVC framework that can eliminate the Clifford overheads. Although there are some gate parallelism issues with that. The PVC itself is still used extensively in many frameworks that is studying the performance and or uh, the proposal of those FTQC designs. For example, in the Litinsky's game of surface code, the PVC is used as the main underlying algorithm representation. So this PVC framework is very important in many of the aspects. Right now, at the time we're doing this work, the only framework, the software package that provides this PVC conversion was from PennyLane. And PennyLane was also using just the graph-based representation for those circuits and then do the PVC commuting and merge apart. So we compared our framework with that. On average, or by mean, we achieve almost a 3 orders of magnitude speed up over the penny. So this shows that how much faster our method really is, and how the powerful the power of those Tableau IRs. So finally, there's this. I want to show this case study for the phase polynomials. I mentioned that uh, one constraint to the same number of qubits, what you can get the best for in terms of the T-count optimization. Perhaps it's just the ZX calculus, and we achieve same T-count as compared to the ZX calculus. But there are also the other family of T-count optimization that is based on phase polynomial. For those methods, however, they do require additional SLF qubits, and those qubits are introduced because phase polynomial uh, only work with a CX plus phase plus T circuit. So you can't have any Hadamard gate in your circuit to work with to use phase polynomial. So if there are any internal Hadamard gates in your circuit, you can do the gadgetization to extract those Hadamard gates out of your gate region. But doing this, you're gonna need additional SLI qubits for those internal Hadamards. So that's why those phase polynomial-based circuit always introduce additional qubit overheads. And for some of them, that can be quite severe. So for example, for this fourth benchmark, originally you only have 20 qubits, 20 logical qubits, and you would need to increase that to 351 logical qubits. But doing that, you can save about 40% of the T gates. So this trade-off will depends on how efficient you can encode your logical qubits and also how costly the magic state factory is. But I'm just want to show this results to see for you to see that on average for this fast taught phase polynomial based method, you can further reduce the T counts by 36%. And for this alpha method, you can reduce by almost 30%, but at the cost of 400% higher qubit counts. So as a summary, so all of the frameworks, the optimizations are actually open sourced in this package called the NWQEC. That is a framework that we developed specifically for the FTQC translations and optimizations. And the two optimization works, the Clifford reduction and Tableau-based circuit, and their corresponding paper links are also shown here. So for the NWQEC, we designed it to be a fault-tolerant quantum computing compilation, so it can compile any of the arbitrary circuits into Clifford plus T and then to the PVC and then do those optimizations. And it does so in a very efficient manner. So it's really fast. We have compared to similar functionalities that is provided from Qiskit or PennyLane. It runs much more faster than those other softwares. And we're actively developing this. So if you have any issues when using this software package, or there are new functionalities you think that's a good add-on to this, and I'm happy to chat with any of those with you. And for it also provides the Clifford NT optimizations that I just discussed. And overall, we have made the runtime efficiency one of the key objectives when developing this developing this software package. So with that, it concludes my talk. Thank you everyone for being here, and thank you for this opportunity. I'm happy to take any questions you may have.